Hello viewers, in the last tutorial we have shown this paper designing, that is the highly sensitive dual core PCF based plasmoning refractive index sensor for low refractive index detection, and I am reviewing this paper. First we have designed in the first tutorial this type of design. Now we will discuss about the result and discussion section. We will find the SPP mode, core mode and SPR. Here is the dispersion curve. We will generate this. So how could we generate this? Just follow the instruction, that is, go to your source file and here is the parameters. In this parameter section there is NA is defined for the refractive index. This dispersion curve is generated for the refractive index of the analyte 1.36. So we will going to put it in this section 1.36. Now we are going for the parametric sweep. Here is the wavelength range, that is the 1.5 to 1.9. So we'll parametric sweep for 1.5 to 1.9, and here is set it 1.5 with the increment of 0.1 to 1.9 micrometer. And how much mode we will calculate? We will calculate for 20, that is enough. So we are going to compute this. After computation we will get this dispersion curve. So let's see how good we made it. So let's begin the compute, and here is the computation process started. It takes some time for the computation process, so we will stay up till the computation process finishes. Okay, after finishing the simulation process, we'll go for the global evaluation, and here we will click evaluate. Here's the evaluation process is running. After finishing the evaluation process, we will, okay, the evaluation process is done. Now we'll find the electric field. Here is the parametric optical value is 1.5 to 1.9. Now we'll find the core mode, SPP mode and SPR. So in the paper we can see that the operating wavelength 1.72 micrometer for the analyte with a refractive index of 1.36. That means at the value of 1.36 and the operating wavelength 1.72, there the effective mode index of core mode and SPP mode intersect. So we should find at the operating wavelength 1.72, and clicking onto this we can see at the point of the intersection the operating wavelength, at the point of the intersection the operating wavelength 1.72, the effective mode index of core mode and SPP mode intersects. We find the SPR. Here is the SPR, we find the SPR. Now we have to find the core mode. The effective mode index of the SPR is 1.4307. 1.4307. Where is the core? 1.4307. 1.4309. Yeah, that's we got 1.4307 effective mode index of SPP mode. If we select this is the effective mode index of SPP mode. Now we are going to make this curve, that is the red dotted line. For making this curve, first we are creating an Excel file in your PC, that is Microsoft Excel. You may say that dispersion curve. First we will select the wavelength 1.5. This is the wavelength WVLENGTH wavelength 1.5, 1.51, 1.52, 1.523, 1.53. Okay, we have written this, the wavelength 1.5 to 1.9. Now we will put the confinement loss, value of confinement loss of this curve. That means at the 1.5, refractive index of 1.5, clicking on and into plot, and this confinement loss for the SPR. This is the core. We have to find the SPR. That is, this is not the SPR. This is not also. We have to find the confinement loss of SPR. That is study one parametric solution. Okay, this is the SPR 1.5. So 1.5367, 1.5. Here is the electric field of the SPR, and it is the value of operating wavelength 1.43, effective mode index 1.4350, and the confinement loss value is 11.340. If we collect this, although this is not same, but we are thinking that this may be equal to something. So at the value of 1.5, the effective mode index is 1.4350 and the confinement loss is 11.340. So we are putting this 11.340. This is the value of confinement loss. Similarly for 1.51, plot 1.51 at the value of 1.514354, 12.870. We have to put 12.870, 1.52. Okay, this is the value for 1.52, 14.703, 14.703, 1.53, 1.53, that means 4349, 16.924, 0.924 for 1.54, for 1.54, 4347, 19.544, 19.544. So you have to do the similar work. You should think that the electric field are aligned in the same direction. That means here it is written that is the Y polarized transverse electric field mode compared to TEX mode. There are two types, TEX and TEY. Here we are calculating the TEX. There is another mode, that is the in 1.54, that is in the both similar direction. This is not a good SPR. We are calculating the only in the X direction, TEX 1.54, and its effective mode index is 1.4347, and it is 19.541. At the value of 1.55 it changes. So you have to find the SPR, that's it, not it, that's it, this is the SPR. So at the 1.55 you will see 4345. This is this effective mode index aligns with this effective mode index, and this is the value of the SPR, 22.816. 22.816. At 1.56 you must see here again changes, so we have to find it. This may be the SPR. Okay, this is the SPR. So at the value of 1.56, 4342, 26.772, 26.772. So at the value of 1.57, okay, at the value of 1.57 it is as it is, 1.4340, 31.692, 31.692. So you have to find all of the value, all of the mode. This is the SPR, 1.58, 1.4337, 37.822, 37.822. So I am pausing my video and calculating all the values for your convenience, so the tutorial will not much more enough. So I can show you that at the wavelength 1.66 the confinement loss is maximum 263.56, and the 1.67, that means 263.65. So in the paper the value of confinement loss should be in 1.72 maximum value, the peak will be in 1.72, but in my work, although I have reproduced it, maybe there are some error, so that the peak of the confinement loss is 1.66. So we are making according to this for showing you the better result, for giving you a concept about it. 176.94, 176.94. That means the value of the confinement loss is decreasing according to this curve. First of all it will increase, and after that it will decrease. So the value of the confinement loss is decreasing, and the peak of this value is found at the value of 1.66. This is the wavelength now at the value of 1.69. Value of 1.69, we find that 142.80, 142.80 at the value of 1.7, 4314, 118.34, 118.3. Here we are at the last stage, that means at the value of 1.89. So we are plotting this graph, plot 1.89. 4266 24.897, 24.897, and the value of 1.9. The value is 4263 24.195, 24.195. You have to see that we have found the peak at this point 1.66, but according to this paper the peak should be in 1.72. I think in my reproduction there may be some error, so the peak is shifted, but it is a concept for producing a new PCF based SPR sensor. All of the figures should be same. That means there will be a value at the peak and there will be a decreasing. So from the figure we can see that if we draw a line graph, we can see that the value is increasing, after that it is decreasing, it is a value. So for plotting the overall whole graph we have to do another work. That means we have to draw the core mode, effective mode index of core mode and effective mode index of SPP mode. We have to draw this line. So how could we draw it again? It is a manual process, so do not think that I am repeating. First of all, we will find the effective mode index of core mode. So we are thinking that this may be the core mode because the electric field are aligned in the transverse electric field in the y direction. So at the value of 1.5, the effective mode index is 1.4358. Here is the value. At the operating wavelength 1.5, this is the core mode 1.4358. So effective mode of core mode, that means the value is 1.4358, 1.4358. Similarly for 1.51, for 1.51, 1.4356, 1.4356. For 1.52, plot 1.4353, 1.4353. This is not the practical core mode because the electric field are aligned in different direction. So we are thinking that this may be the core mode. This is not the core mode. We are thinking that this is the core mode because the electric field are aligned in the same direction. For the 1.53, we are plotting this 1.4351 effective mode index is. So 1.4351, that is the effective mode index 1.43. For the 1.54, the effective mode index is 1.4349, 1.4349. So I am plotting this according to 1 point up to 1.9 by pausing my video. So at the last of this 1.89, that means at the 1.89, the value of core mode is 1.4265, 1.4265, and at 1.9 the value is 1.4262, 1.4262. Here you will see the value is gradually decreasing 1.4358 to 1.4262. In the figure, the green line shows that with the increasing of the wavelength, the value is also decreasing. Similarly, similar for the equation. This is the effective mode index of core mode. but we have to find again effective mode index of SPP mode. So what will be the value of SPP mode, effective mode index of SPP mode? Here will be the effective mode index of SPP mode. We will not select all the value for the SPP mode. Here you can see there are several values, all the several values for the SPP mode. So how could I find? We may take maximum from 1.62 to 1.72. From 1.62 we may take 1.62 because the peak is in 1.66. So we are going to plot this. This is 1.62. So we have to find the SPP mode, effective mode index of SPP mode. First of all, we have to find the SPP, that is what is the value of SPP. SPP occurs here, so we may see that if this is the SPP, not this is the SPP. If it is the SPP, that is value of 1.4347, we collect it 1.4347 for 1.63. The value will be 1.4342. 1.4342. You have to identify by yourself by watching the SPP. It is SPP or SPR. 1.4337, 1.4337. That is, it is also decreasing. 1.65, 1.4331, 1.4331, 1.66, 1.4325, 1.4325, 1.67. This is not the SPP. We may 1.4312, 1.4312. This is not 1.432. This may be 4312, 1.4312, 1.4312. Okay. For the value of 1.68, we may find the SPP 1.4306, 1.4306, and the value of 1.69, we may find that 1.43, that is 1.43. We're taking not lot of value for the SPP. 1.4295, 1.4295. At the value of 1.71, we may find that 1.4289, 1.4289. Okay. You may see that the effective mode index of core mode is gradually decreasing with the increasing wavelength, but it decreases in a rapid pace. The value of effective mode index is decreasing higher rate than the effective mode index of the core mode. So for making this type of curve, that is the dispersion curve, we should select the total file. Here, click on to insert line graph, and we will find this type of curve. Now we are setting the value, that is minimum value is 1.5 micrometer and maximum is 1.9 micrometer, and hit the enter button. We have find our dispersion, that means the confinement loss curve, and here is the effective mode index curve. Just clicking onto this, you have to select the secondary axis, and again clicking onto this, we have to select the secondary axis. So after analyzing this, we may find that This curve is our dispersion curve. This curve is gradually increasing. It is the effective mode index of core mode, and this brown color curve or ash color curve is the effective mode index of SPP mode. You may see that they are intersects at the peak point. Although this ash color curve is not perfect, because at the point of the intersection, at the point of the peak point, the effective mode index of core mode and SPP mode must be equal. So here is our dispersion curve, just like this. Now I will clarify a simple thing, that is the SPP mode, core mode and SPR from this image, from this model. This is the core mode. You have to identify by watching it, and electric field around it. All of the electric field will be in the same direction, either it is in the x axis or y axis. And this is the core mode. If we remove the electric field, if we disable it, if we disable the arrow surface, then you will find this core mode is equal to same as this. Again, for the SPP, how would you find it? For the SPP, the entire electric field is confined to the plasmonic layer, that is this point, that may be this point here, that may be this point. You have to identify by checking it. In every PCF based SPR sensor there will be metal, the SPP will be in the metal. And how do you find the SPR? At this point, the core mode and SPP mode will be intersect with each other, that is the electric field are in the opposite direction. So we are not taking this. You may take this. This may be a SPR, because the electric field is in the same direction. So if we disable this, that means it looks like the SPR of the PCF sensor. So this is the main tutorial for the dispersion curve. Now here is the curve, that is the loss spectra of the sensor. You may make this curve 1.29 to 1.38 by changing the refractive index of analytes. That means you have to change from 1.29 and hit the enter button. You have to calculate it from the range of refractive indices and the compute button, and again you have to repeat the same procedure for making this type of curve. So from 1.29 to 1.38 you have to simulate this model by only changing the refractive index at least 10 times or 11 times. So 11 times, after 11 times simulation, you will get this type of curve. For every analyte of refractive index you have to calculate, you have to find the same procedure. So again here is a D1, D2, D3, D4 and the pitch. So how could you find that? You have to change the value of D1, that means in the parameters section, if there is a value of D1 1.70, you have to set this 1.70 and hit the enter button. In the parameter section or component section, you have to change the geometry. That means select the build all. After that it will change. Here will be the parametric sweep. Again you have to calculate d1 1.70, that means the red color. You will find a peak. Similarly for the same condition for all of this. And how could we find the amplitude sensitivity of the loss curve? Here the value of this sensitivity curve is shown from 1.34 to 1.39. so you may find this by getting the value of 1.34 confinement loss curve from confinement loss curve. So there is an equation of amplitude sensitivity. So we are going to implement this. Now we are going to plot this amplitude sensitivity curve according to this equation. It is very much easy to calculate the amplitude sensitivity as it is given to this example. So first of all, what you have to do, you have to find the loss curve of the refractive index of 1.34, and it is already done if you have this curve. So from this value we may calculate this amplitude sensitivity curve. How could we calculate? From the Excel sheet, suppose you have a value like this. The confinement loss of the refractive index of the analyte 1.36 is given here, and the 1.37, 1.38 and 1.39 is given here. Here is the wavelength. So how could we calculate? First of all, you have to give equal and first bracket, selecting onto this value minus this value divided by 0.01 into this value, and hit the enter button. You will find a value. This is the amplitude sensitivity of this sensor, and just click onto this. Similarly, you have to do the same work for the this value minus this one divided by 0.01 into this one. Hit enter, and these are the values of the amplitude sensitivity. So for plotting this, we have to select minus this one divided by 0.01 into this one. So selecting this, and these values are calculated. Here is the wavelength of this sensor. Okay, so you may not calculate the maximum value of the analyte of this refractive index. So if we want to see the amplitude sensitivity of the sensor, just selecting on this, again insert, again and align. Here is the amplitude sensitivity of your sensor. So you may change it by changing the same option. You may change it by changing the same option again. In the negative portion, there is the amplitude sensitivity curve. Here is the value. So minimum value is given here 1.5. You may change it to 1.6, and the maximum value is set to 1.8. Then your curve will be much more clearer. So this is the procedure for drawing the amplitude sensitivity of this curve, and all of the equations are very much easy to calculate. And after all, you have to set your comparison. Here is the overall scenario of reproducing the curve. Here is the polynomial fit, that means the resonant wavelength of your sensor. So this is the part of the session, and thanks to all, and Allah Hafiz.